All right, so our Taylor series here, of course, ties directly into the Taylor polynomials that we took a look at on Tuesday. We're going to be looking at both the Taylor and the Maclaurin throughout this. Just a side note that I added for myself. Textbook didn't directly say this, but I think of a Taylor series simply as a Taylor polynomial that I am able to establish a pattern for, or a coefficient pattern for, and then write it as a series. So that's what's happening. The expansion of the series would then resemble what the Taylor polynomial looked like in section 8.4. Okay, so those coefficient terms that are dependent upon the nth level derivative would then be able to be streamlined into the series version of Taylor. Okay, so essentially we'll be looking at different functions. We'll be saying, can we write it as a Taylor polynomial and also as a Taylor series? So we've already investigated some of the most common ones. We've looked at the e, we've looked at the sine and the cosine, and then a couple of other ones in the last section. We'll continue to do so here. So we're going to combine the idea of a Taylor polynomial with a Taylor series in this section. We're also going to look at if we've proven something about a basic function like e to the x, can we use that Taylor series to then look at something that's a little bit more complicated? Okay. So that's kind of the extension of this section. Much of it will seem similar, and then there's obviously things that we're going to add into it. Okay, so that summarizes this page. Everything here is just from the textbook. There is a proof on Khan Academy. I think I included those links already. If I have not, I will do so when I upload this video. Okay, so the first one that I chose to leave filled in just because it was a lot of writing, and I think it is pretty easy to explain as you look at it. Find the Taylor series for f of x equals x to the negative third centered at c is equal to 1. Okay. So I listed out my derivatives, f prime, f double prime, f triple prime, and I was able to establish a pattern, f to the nth derivative, because it's a power rule. So then each exponent's coming down, so it looks like a factorial out in front. The sign will alternate because we are beginning with a negative exponent, right? And the exponent will continue to decrease by 1. So I was able to streamline this derivative and come up with a rule. Okay. Only 1 and 2 are missing from that coefficient portion, right? Because it started as a negative 3 exponent. So that part that's written as 3 times 4 dot 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 to n plus 2 could be written as a half of n plus 2 factorial. The half part is dividing out the 1 and the 2. Okay. So I can further streamline this and write f to the nth derivative at 1, because that's our center, would then be negative 1 to the n power times n plus 2 factorial over 2. And then continuing to use that trick that if you have an n plus 1 or an n plus 2, etc. factorial, we can write it with respect to n factorial. And the reason we would choose to do this is because then when we put it into the a sub n term for our series, we'll be able to cancel that n factorial out. So n plus 2 factorial is equivalent to n plus 2 quantity times n plus 1 quantity times n factorial. So if I look at the coefficient only, and I figure out, well, what is my a sub n in this Taylor series, it would be f to the nth derivative of c over n factorial by definition. I could plug in that negative 1 to the n power n plus 2 factorial, divide it by 2, because we had that in our other rule, the 1/2, times n factorial. Canceling things out because n plus 2 factorial can be rewritten. The n factorials cancel. So this is my coefficient term for my Taylor series. So if I did the expansion as I would have done it in 8.4 just as a polynomial, right? 8.4 said, well, f of a plus f prime of a times x minus c to the first power, so that's our second term. Then we had plus f double prime of a, x minus c to the second power over 2 factorial, etc. So the Taylor polynomial on the left-hand side on the bottom of the page there is written out the same way that we did in 8.4. But I can, because I was able to come up with that a sub n so nicely, I can write it as a Taylor series and kind of squish it back together. It's a summation from 0 to infinity, negative 1 to the n power to get that alternating sign. N plus 2 times n plus 1 is all that's left of the factorial term, divided by 2. The 2 again is because we were missing the 1 and the 2, because it started as an x to the negative third. And then we just multiply it by the x minus c, or 1 in this case, to the n power. Okay, so that's the process to take some function. We could write it as a Taylor polynomial one step at a time, but when we can establish that pattern, we can then write the coefficient term a sub n and put it into a Taylor series. I'll leave this page up for a moment. I'm just going to pause the video. Okay, so theorem 2, this is speaking to essentially the validity of each individual case, right? There's no guarantee that just because we find Taylor that it definitely converges to F. In section 8.4, we investigated a little bit at the end that error, and I think, Mullen, you had asked a few questions about that and others as well. How close is close enough, basically, right? Where is that error going to be small enough for us to say that this is an acceptable approximation? And that changes based on the degree or the order that we go to, right? So similarly, we need to take a look at the error in order to say whether or not a Taylor series does in fact converge back to the original function, right? The whole big idea here is to say, well, I've got this function cosine or e or something along those lines, and I want to see, can I come up with a polynomial that mimics this for some range of numbers, for some radius of convergence? That's our goal here. And if we can do that, then literally if we graphed them, they should be on top of one another for some interval. So what this theorem is saying is if and only if, right? I wrote it over here, that there's no guarantee that t of x converges to f of x, but if the remainder r approaches 0, then t of x converges to f of x. And remember that that r is basically, it's the difference between the actual function and the Taylor polynomial at some order k. So the limit as k approaches infinity of r has to be 0 in order for us to say that the Taylor series converges to the function. And then that's where this theorem comes into play. So we're going to say that we have an interval, right, some radius of convergence centered at c minus r comma c plus r, where r is greater than 0. We're going to suppose that there's some k value larger than 0, such that all of the derivatives of f are bounded by that. To me, this kind of resembles like a squeeze theorem idea, right? So for example, functions that are going to work out for us, sine and cos, right? They're around 1 and negative 1, so this will hold true for that. It'll be easy to do that. Even e, right? Because at a certain value, e of 0, it's always going to equal 1. So there's certain times where we can prove this, and this really is speaking to those special cases that we need to prove, and then it'll follow through. So we'll take a look at if the absolute value of the derivative of f to some order k is less than or equal to big K, then we can say that f is represented by the Taylor series for all x in the interval. right, so for the first example here, demonstrating this theorem. Again, this theorem is specific to cases that we can really prove that have this very, very clear-cut bound. Right? The absolute value of it has to be less than k, okay, for all derivatives. So for example, the expansions of sine and cosine. Let me zoom. Yep, there's still a delay. Okay. Sine and cosine are given as is. If you recall, we proved them in 8.4, and we saw that there was that alternating thing happening where it went from, you know, a 1 to a 0 to a -1 to a 0, etc., because of the way the derivatives go back and forth with sine and cosine. So we were able to show that the sine expansion, all of the evens zeroed out, and you're left with all of the odds, odd degree terms. And with the cosine expansion, the odds went to 0, and the evens were left because of, you know, when does at sine of 0, right, that's equal to 0, etc. So when does the derivative end up with a sine versus a cosine? So that explanation is written here. We already went through that, so I didn't go in great detail, but basically the derivatives and values at x equals 0 form this repeating pattern. Sine x is 0, cosine x is 1, etc. So all of the even derivatives, and this work is accounted for if I start with sine as my original. So all of the even derivatives go to 0, and all of the odds alternate in sine. So we're able to write that coefficient term as a sub 2n plus 1, representing all odd numbers, are -1 to the n power over 2n plus 1 factorial. So that's that coefficient term. And if I looked at it for cosine, if I began this list with cosine and then worked downward, it would be the reverse is true, right? The evens are left, and it would be -1 to the n over 2n factorial. Okay. So by theorem 2, this is true because we know that all of the derivatives are going to be smaller than some k. Specifically, k can be set to 1. And then therefore sine or cosine, whichever one we're looking at, does satisfy this. This would be true for any r. They basically say that r is arbitrary. It does not matter. I'm sorry for the sloppy handwriting. And therefore sine and cosine converge to t of x. Okay, so this isn't something that you'll have to prove. This is something that is accepted. Sine and cos Taylor series do converge to themselves. Right, the Taylor series for sine converges back to sine. The Taylor series for cosine does converge to cosine. The approximation is accurate. Okay, so example 3, the Taylor expansion of f of x equaling e to the x at x equals c. So in general, we're looking to find it, right? That's all that the question is. So we can make a statement that f to any derivative, f to the n of c, is still going to equal e to the c, no matter what level we're at. Doesn't change for all x values. So then we can jump to the conclusion that the summation, like the rule for Taylor series, right, is summation from 0 to infinity of the f to the nth derivative of c, which always equals e to the c, over n factorial times x minus c to the n. And that's our Taylor series. And we know that this is going to be true based on this information that I've written down below it. So e to the x is always increasing for all r's greater than 0, right? So then the kth derivative of f, the absolute value of that, is always going to be smaller than or equal to e to some c plus r. Because the left-hand side is e to the c, which would then be smaller than e to the c plus r as the exponent increases. This would be true for any x belonging to that interval. So if k is equal to that e to the c plus r, right, that's a set value, then we can make the statement that t of x converges to f of x for all values in that interval. And written down below as we've seen it, that's the Maclaurin series centered at 0, which is going to be commonly used in examples. So 1 is your f of 0, then you have f prime of 0 times x minus 0 to the first power, etc.
Can you go over the thing about how like e to the x is increasing and then the absolute value of f, the kth derivative is less than or equal to e to the c plus r?
Sure. So the main thing here, in order for theorem 2 to work, is you have to have that bound. So because e to the x is something that doesn't change, right, we're able to make a very concrete statement here. So any level derivative, the absolute value of it, is going to remain e to the x. And therefore, if we evaluated it, it would still be whatever e to the c is. And if we are increasing our radius, right, plus or minus that r, then the absolute value of the derivative term would always be smaller than the e to the c plus r, because c plus r is going to be a larger exponent than what we would have on the left, which would be just e to the c. So because we can make that statement that we're completely bounded by this k value, so we call k e to the c plus r, some number, then we can make the statement further that it converges to f. The main thing is, can we say that it always stays less than this k? Or does it go off forever? Right? If it goes off forever, it's divergent, right? It is not convergent to our f. But the trig, the e, we're able to make these statements. So example 4 says, find the Maclaurin series for f of x equals x squared times e to the x. So if I began this blindly, and I was like, all right, well, I guess I need to do f at 0, and then f prime at 0, and then f double prime, etc. at 0, I'm going to have a product rule. And that product rule is going to continuously get more complicated at each level of the derivative. So it's not that you couldn't do it, it would just be more complicated. So we can use the knowledge, use what we know. Right? We've already proven the e to the x. We've already proven the sines and the cosines. So we can use those. Those are accepted Maclaurin series. So we can say that this function, right, is then, whoops, I didn't mean to write it like that, equal to x squared times the accepted Maclaurin series for e to the x, which again, I mean, I keep drilling it in my head every time because I'm like, where the heck did that come from? Right? The 1 that comes from f of a, or f of 0 specifically. So e to the 0 is 1. Plus.
Are you writing?
Yes, I am writing. So that next term, which is just an x, that comes from f prime of 0, which is still 1, and then x to the first power over 1 factorial, etc. And then we end up getting the x squared over 2 factorial, or 2, plus x cubed over 3 factorial, and so forth. Right? I'll just write one more term. Right. X squared is already a polynomial. I don't need to do anything with that. So now all I have to do is multiply it in. So I get my x squared, I get x cubed. Oops, that's not supposed to be x to the 4th over 2 plus x to the 5th over 3 factorial plus, I'm going to write this as factorial, plus x to the 6th over 4 factorial. Okay. So now can I write this as a series? Sure. So it's starting with a degree of 2. It's going to infinity. If I look at my exponents, right, they increase by 1, 2, 3, 4. So I can just write this as x to the n. Divide it by, if I look at my factorials, notice that under the 4 exponent, it's a 2. Under the 5 exponent, it's a 3. So it's 2 less. So I would write this as n minus 2 factorial. Okay. So find the Maclaurin series for e to the negative x squared. So because the Taylor expansion of e to the x is already valid for all x's, right, we can just use substitution here and prove the same thing for e to the negative x squared. So rather than just having an x in our formula, we put a negative x squared in there. It's like a u sub, essentially. But we don't have to do the full expansion. Right, so instead of just having the x to the n, we have the negative x squared quantity to the n over our n factorial, which could be written as, if we pull out the negative 1 for the alternating, then we're left with an x to the 2n over an n factorial. And I like to write them out. You don't really have to here, but when you write it out, I think you really start to see with how did that negative x squared truly change the terms, because I think over time you're going to get pretty used to the Taylor expansion for e to the x. So this one, right, e to the x starts with a 1, and then it would be a plus x, but instead now it's a minus x squared. And then it's a plus x to the 4th over 2 factorial. All right, and if I actually did it while thinking about this summation instead of just doing it out of memorization, I would still get the same thing. Of course, if I put in 0 here, negative 1 to the 0 is 1, x to the 0 is 1, 0 factorial is 1, so that's where my 1 term still comes from. If I put in a 1, I'm going to have a negative is going to stay, x squared over 1 factorial, so I do have my negative x squared. If I put in 2, I would go positive 1, x to the 4th over 2 factorial, etc. I would keep on going. So my next one will end up being negative x to the 6th over a 3 factorial. So all that happened here is I took the proven Maclaurin series for e to the x, and I replaced the x's with a negative x squared because it's already been accepted for convergence. Okay, so example 6 is using integration in order to find the Maclaurin series for f of x equaling ln of 1 plus x. So we've seen the integration used a lot when we're using the ln's. That was one of the examples in the section when we covered the integration process. So that's one giveaway that we're going to do that. And then the connection between integrating and ln's is it turns it into 1 over the inside. And that 1 over the inside actually resembles the answer, I'll say, for the geometric series. Okay? So this question, the starting point is saying, well, let's look at this geometric series with r equaling negative x. Because if r equals negative x, and recall that the summation from n to 0, n equals 0 to infinity, of r to the n power is equal to 1 over 1 minus r, when your r is less than 1. So therefore, this will be valid when the absolute value of my x is less than 1. Right, because this relationship for geometric is true for smaller than 1 values. Okay, so then specifically to the problem that we're looking at, then we have this summation of negative x to the n, which is equivalent to 1 over 1 plus x. And now it starts to look similar, right, because the integral of ln of 1 plus x equals that. So I'm going to expand this. Right, this would be equal to 1 if I did negative x to the 0 power, and then it would be a minus x if I did negative x to the 1st power, and then it would be a plus x squared, and a minus x cubed, and so forth, if I just expanded that geometric series. Okay. So this is kind of like setting the stage for what we need. Now, if I look at my ln of 1 plus x, and I say, well, that's equivalent to the integral of dx over 1 plus x, right? They go back and forth. So if I'm integrating that geometric, the 1 over 1 plus x, sorry for the dogs, then I can, right, I'm integrating this, let me highlight it. Then I can also integrate this and make an equivalent statement, a further equivalent statement. So the integral of 1 returns to an x. The integral of negative x returns to negative x squared over 2. The integral of x squared returns to positive x cubed over 3, and so forth. Negative x to the 4th over 4. So I took this and I put it into an integral symbol, and therefore I took this and I integrated that. All because the integral of that geometric is equal to ln of 1 plus x. All right, so now it all comes back to, can I establish a pattern so that I can write it in a summation? Can I come up with that coefficient term? Or the whole thing, really, but the x part is the x minus c to the n power. So this is equivalent to, I'm just going to write this bigger because I don't need to squeeze in so much. This is equivalent to the summation from 1 to infinity. Oops, you know what? I do want to write one more thing before I write that. I want to include, the textbook didn't do a good job of this, I want to include the c right there. Because if I'm integrating, I really should have some constant. But, as a side note, c equals 0 here because ln of 1 plus x equals 0 when x is 0. So therefore, when I do my summation, I'm starting it at 1, right? The 0th term, this is gone, okay? So therefore, my summation is going from 1 to infinity. I'm noticing that I have my alternating positive negatives. But in order to make sure that they're alternating the right way, I need an n minus 1 up there. Right? Because if I'm starting at 1, then the 0th term technically is positive. And then the remaining part is the x to the n. And the denominators are just n's. This is valid only for the same restriction that we had before. Right? Beyond that, it's not going to hold true. Okay, so this example is saying multiplying Taylor series. Right? Again, use what you know. Write the terms up to degree 5 in the Maclaurin series for f of x equaling ex times cosine x. We know both of them. We're not going to reinvent either of them. We're just going to pull them down and multiply them. No proof here, nothing necessary. So the e to the x is the 1 plus plus x squared over 2. factorial technically, but I'm going to write them as true numbers right now just to save some time, plus x cubed over 3 factorial, or 6, plus x to the 4th over 4 factorial, or 24, plus x to the 5th over 6 factorial, or 120. So that's the first, or up to the 5th degree, I should say, of the e to the x. The cosine is the one where the odds are 0, so we only have in the even degrees, even terms. So they would be 1 minus x squared over 2 factorial, or 2, plus x to the 4th over 4 factorial, or 24. All right, remember that the coefficient terms are either 0 or 1, or -1, for trig, sine, and cosine. So therefore, these are just as simple as the e to the x terms are. Okay, except for the signs alternate. I'm missing odds. I stopped at the 4th because the next one is going to be the 6th, so I don't need it. So now, this is purely a tough, but an Algebra 2 question. Now I'm just multiplying them all together. And because they only went up to degree 5, as I multiply them together, right, I'm going to eventually get like an x to the 9th. I can ignore it. I don't want it. It only went up to x to the 5th. So I did expand the whole thing. I'll put it in here so you can see what it looked like. Just write it quickly. So I have 1. So the first, I'm taking the whole first set of parentheses, e to the x, multiplying it by 1, then multiplying it by negative x squared over 2, then multiplying it by x to the 4th over 24.
Would it be possible just to do the summation notation so you don't have to expand?
You try and share with me. I'm not saying no, I'm just not sure. So as I multiplied it out, I kept all those terms and then acknowledged afterwards that I wouldn't need them. It's just easier for me to stay organized. Okay, so there's all of the terms. I'm going to now cross out the ones that I don't want. Okay. So when I do everything, the 1 has nothing to combine with, the x has nothing to combine with, the x squared over 2 minus the other x squared over 2, that's actually gone as well. Then I have a negative if I add the x cubed over 6 minus the x cubed over 2. Then I would have a negative x cubed over 3 left. And if I do the 4th degree terms, I have an over 24, and then I have a minus over 4 and a plus over 24. That simplifies to a minus x to the 4th over 6. And the x to the 5th terms simplify to a minus over 30. So that would be your final answer because we're only taking up to degree 5. So example 8 is asking us to use an integral for sine of x squared and express it as an infinite series. Right? So the first thing we want to acknowledge is that we've already proven the Maclaurin expansion is valid for all for sine x for all x. So we have a little bit of a twist on it. We have an x squared in there instead of an x. That's the first thing we want to explore for part A. So we know that sine x is equal to the summation from 0 to infinity, -1 to the n power, 2n plus 1 factorial x to the 2n plus 1s, right? So the even terms for sine zero out, the odd terms follow through. So now, what if we want to look at the x squared? So sine of x squared would be equal to the summation from 0 to infinity, negative 1 to the n, over 2n plus 1, all that stays the same. But now the exponent, we are squaring that 2n plus 1, or turning it into a 4n plus 2. So that's the important part here. So if j is equal to the integral from 0 to 1 sine of x squared dx, right, and we want to express this as an infinite series, then we can say that this is also equivalent to, first of all, the coefficient portion can come out in front of the integral. So that would be the negative 1 to the n over 2n plus 1 portion of your summation. And we're going to multiply that by the integral from 0 to 1 of x to the 4n plus 2 dx. So when we are integrating that portion, right, remember this is bringing us back to f of b minus f of a. So side work over here, the integral from 0 to 1 x to the 4n plus 2 dx. Right, it's a power rule, reverse power rule. So we're adding 1, we're dividing by the new. So it's x to the 4n plus 3 divided by 4n plus 3 from 0 to 1. So if we evaluate this at 1, we would have 1 to the 4n plus 3 over 4n plus 3 minus, evaluated at 0, would be 0 over 4n plus 3. So the 1 to the 4n plus 3 is just 1 over 4n plus 3. So then we can say that this whole thing is equal to the summation from 0 to infinity, negative 1 to the n power over 2n plus 1 factorial times 1 over 4n plus 3, which is equivalent to, the first few terms would be a third, right? If we put in 0 and simplified everything, it would just end up with this 1/3 minus 1 over 42. Again, evaluating that that term at n equals 1 plus 1 over 3, 13, 20. And listing out these terms, I suggest pausing the video and going through and actually calculating them yourself and seeing how the things work out. So part A is done, right? There's our infinite series. Part B says, well, determine j to within an error less than 10 to the negative 4th. Well, it was helpful that we listed out the first 4 terms because, first of all, we know that j is alternating with decreasing terms, right? So that's important to acknowledge. So in previous lessons, we've shown in these cases that the sum of the first n terms is then accurate, right? With an error that is less than the n plus 1 term, or the next term. So therefore, since we've already got the 4th term, which was negative 1 over 75,600, and that is less than 10 to the negative 4th, then our approximation using the first 3 terms is good enough. The next topic in this section that we're going to cover is the binomial series. Taking that binomial theorem as you've seen it and applying it to series. So So for any exponent a, and where the absolute value of x is less than 1, so that's our center, 1 plus x to the a power is then going to equal that expansion. So find the terms through degree 4 in the Maclaurin expansion of f of x equaling 1 plus x to the 4/3 power. So in this case, a equals 4/3, and we're just going to follow the theorem. So I'm going to first list out what my coefficients would be, because that's the challenge. So the first one is just a 1. And then we have an a, or 4/3, divided by 1 factorial. And then we have an a times an a minus 1 over 2 factorial. And then we would have an a times an a minus 1 times an a minus 2 over 3 factorial. And the last one would be an a minus 1, a minus 2, a minus 3 over 4 factorial. Right, so simplifying all of those, we would still have our 1, we would have our 4/3. Here we have a 4/3 times a 1/3 over a 2, which is going to be a 2/3. We have a 4/3 times a 1/3 times a negative 2/3 over a 6, which simplifies to a negative 4 over 81. And then we have a 4/3, a 1/3, a negative 2/3, and a negative 5/3 over a 24, which simplifies to a 5 over 243. So that means that this expansion is approximately equal to 1 plus 4/3 x plus 2/3 x squared minus 4 over 81 x cubed plus 5 over 243 x to the 4th, and so forth. Okay, so one more example using this binomial series again, but this one's a little bit more complicated because it's starting with something that is more complicated. So we're going to take a look at a simpler example, right? Because again, the series works for 1 plus x, and we have 1 minus x squared, right? I could start by writing this as 1 minus x squared to the negative 1/2, but it's still not exactly what it works for. So I'm just going to consider 1 plus x to the negative 1/2. So thinking again about our coefficients only, so we have a 1, we have a negative 1/2 over a 1 factorial, right? So in both of these cases, a is still negative 1/2. We have a negative 1/2 times a negative 1/2 minus a 1 over 2 factorial. We would have a negative 1/2 times a negative 1/2 minus 1, negative 1/2 minus 2 over 3 factorial, and so forth. And we're going to see if we can come up with a pattern here. So I have 1, I have negative 1/2. This is a negative 1/2 times a negative 3/2. Right, so that works out to be, and simplifies along with that 2 factorial in the denominator. I would have a 1 times a 3 over a 2 times a 4. Right, let me do side work just to show that. So you can see how we're left with the 1 and the 3 up top and the 2 and the 4 on the bottom. This pattern is something that's going to continue, and we're going to end up with a negative 1, a 3, a 5 over 2, 4, 6. The most important thing with the signs is just observing that they do alternate, of course. Right? So our pattern for this negative 1/2 over n going to be negative 1/2 right in the beginning. Starts like this. And if you notice, we could write that as negative 2n minus 1 over a 2. It's negatives out in front. And on the bottom, because it's just factorials, we have 1, 2, 3, up until n. So I can write this as negative 1 to the n power of 1, 3, 5 until 2n minus 1 over 2, 4, 6 until 2n. Okay, so this is valid for x is less than 1, absolute value of x is less than 1. Right, based on our theorem. And if we've proven that the 1 over square root of 1 plus x equals, what we just showed, then we can jump to the 1 over square root of 1 minus x squared, right? So, first of all, 1 over square root of 1 plus x is equal to 1 plus, all right, we don't want to forget about that 1 that didn't quite fit the pattern. Summation beginning with 1 going to infinity, negative 1 to the n power, times 1, 3, 5, up until 2n minus 1 over 2, 4, 6, up until 2n to the x to the n. So that was true, and you could expand each term, right? That would end up equaling 1 minus a half x, right? Using the coefficients that we found up top, plus 3/8 x squared minus ... We can then substitute, because if this is true, then this is also true. So we can just substitute negative x squared. And finally, we can arrive at, I'll change color so it stands out a little bit better, 1 over the square root of 1 minus x squared is equal to 1 plus the summation from 1 to infinity of that same coefficient x to the 2n. So significant change here is I dropped the alternating sign because now we have that even power, right? So these terms would come out to be 1 plus a half x squared plus 3/8 x to the 4th plus etc. Okay, so that's the end of this section. Remember, big picture, we're looking at these Taylor series, we're looking to see, do they converge to the Taylor polynomials, do they converge back to the original functions? The more accurate, or we can get more accurate by increasing the amount of derivatives that we use in order to find our Taylor polynomial and terms in our Taylor series.